Hello, I'm your track host for tonight, this afternoon. I'm Puya from Giant Swarm, and the next talk is going to be about scaling service endpoints. It's going to be by Wojciech Tyczynski, right? And Minhan Xia from Google.
Okay, thank you. Thank you for introduction. So, just to add to this, like Minhan is focusing mostly on networking. I'm mostly focusing on performance and scalability. And the effort that we are going to describe today is a joint effort between those two special interest groups and those two teams. But before we describe the effort itself and what we are doing, let's try to understand what the problem actually is and what we are trying to solve. So there are basically two main problems that users are facing currently in this area. The first one is that there is a limitation for the number of endpoints that you can have in a single service. I will talk a little bit more about both of these in the next slides. And the second problem that users are observing is that they may observe significant performance degradation, especially in very large clusters when using large services. So to give you an example, changing even a single endpoint in a 5,000 node cluster, if a service has 5,000 endpoints, may freeze the control plane for a couple seconds completely. So where are those coming from? What is the reason for those problems? The root cause of both of them is actually lying in the Endpoints API. The Endpoints API is has been designed in very early days of Kubernetes when scalability wasn't really a concern. People weren't thinking much about scalability implications. And to be more specific, the actual reason although the actual reasons are different in those two problems, the root cause for both of them is the problem that the endpoints object contains a list of all endpoints inside of that service. So let's try to understand where are those coming from and what is causing them. So let's say that we have P backend pods in a service. Then as I mentioned in the previous slide, the size of the endpoints object is proportional to that P. That means that with roughly 5,000 endpoints, it depends on how long the length of the name of those pods are and how long is the name of the namespace and stuff like that. But with roughly 5,000 endpoints, we are getting to the point where endpoints object has 1.5 megabytes of size. And what does it mean? There is also a limitation in etcd level for the maximum length of the value in the object stored in etcd. And it's exactly 1.5 megabytes. This value is configurable, but increasing that actually changes performance characteristic of etcd, makes it a little bit worse. So it's not something that we really want to do. So basically, to summarize, this limitation for the number of endpoints in a single service is a consequence of a limitation at the etcd level for the length of the value that is stored in etcd. So let's take a look into the second problem that I mentioned a couple minutes ago. But before we get there, let's try to understand how the service workflow actually looks like. So I will focus on the case where we add a pod to already existing service, but all the other cases like deleting a pod or anything like that is pretty analogous, so you will understand it. So let's say that there is already a service created, and we are creating a pod. So what's happening now? The pod is being picked by scheduler and scheduled. What is happening then is that kubelet is watching all the pods that are assigned to it. Then it's doing all the necessary work to start the pod, and when it's started, the green lines here means that it's within this dimension. It's already done. So this means that here that the pod is already started in the container runtime. The pod is then, once it's started, kubelet is reporting it as ready and as running via Kubernetes API. What is happening there is that endpoint controller is watching all the endpoints in the system, watching all the pods in the system, and based on the fact that this pod just became ready, it's updating the endpoints object corresponding to our service. And what is happening then is that there is like an agent called kubeproxy that is running on every single node that is basically responsible for implementing a service concept in Kubernetes cluster. And what it does, it basically watches all endpoints in the system. And based on that information, it's programming IPtables or IPVS or whatever other mechanisms you are using. And that basically finishes this flow of adding a pod to a service. That like all the lines are green, so everything is programmed. So where is our problem actually coming from? What is causing it? So as I mentioned, like there is like a kubeproxy running on every single node, and all of those are watching all the endpoints in the system. So what does it mean? It means that if there are n nodes, there's also n watchers watching for every single endpoint in the system. In the current implementation of API machinery, every watcher is treated independently. So that means that to send a watch event to watcher, you need to like serialize it independently for every single watcher, copy it and stuff like that. We are also trying to address that independently, and this is something that is already happening. But even if we fix that, the amount of data that we need to send to all the watchers like doesn't change. So let's focus on the aspect of like how much data we need to transmit to watchers. So as we already discussed, like the size of the endpoint object is like proportional to number of backend pods. There are n watchers, so the total number of total bytes transmitted per update is proportional to the multiplication of those two. So let's take some examples. So let's say that we have 5,000 nodes. The size of the endpoint object is like 1 megabyte. Let's assume that this is like for 5,000 endpoints in the service. So that means that we basically need to transmit like 5 gigabytes of data, which is roughly 50. And this is just for an update of a single pod in that service. So what if we are rolling update? We are doing rolling update of a service. That means that since we assumed like 5,000 endpoints, it means that we will send roughly 5,000 updates to every watcher. Times like 5 gigabytes, it gives us like 25 terabytes of data to just do rolling upgrade of the service. So I think it's pretty clear now that like what scale we are talking about and what problems we are facing, and it's pretty clear that in order to get to higher scale, which Minhan will be talking about now, we need to do something here. So yeah, so I'm handing off to Minhan now.
All right, thank you, Wojtek, for laying out the problem space. So let's focus a little bit on the user side. So what does the user want? The user wants to run large services with thousands of endpoints, and it will want to run it in a large cluster with thousands of nodes. And then user want to be agile. It wants to deploy, roll out their services frequently, or they wanted to canary or whatever use case. So that translates to high churn within the service. So all these should work without extra caveats. This should just work. Well, when we start looking for the solutions for the scalability problem we are trying to address, during the brainstorming, we identified several directions we can take, right? First, we say, what if we just enhance the API machinery and to optimize for certain cases? Or we add some kind of dynamic batching or rate limiting mechanism in the service endpoint update pipeline. And what we quickly realized that these alternative approach can get complex very quick, and it's not without downsides. So we decide that basically tactical changes will only help a little bit. It only pushes the scalability threshold a little. And what we really need is something fundamentally better, that is to redesign the API. So our goal of the redesign is to support tens of thousands of endpoints in a cluster with thousands of nodes. And at the same time, we wanted to enable future extensions. In comparison, the current recommended scalability threshold for service backend is 250 endpoints behind a service before you get into performance degradation problems. And our goal is to 100x that scalability threshold. So we have a few guiding principles for this redesign API. So scalability has many dimensions. It's mostly trade-offs, and we can even drill down to deeper into one dimension, for instance, CPU. You can say, hey, we wanted to optimize CPU usage on the master or on the nodes based on whatever algorithm you use or the pipeline you choose. We can shift the load between master and the nodes. So there are many trade-offs we can do. But the goal is that if the system scale grows, the number of nodes grows, the number of services grow, the number of endpoints grow, all the dimensions should scale with bounded increase. And a counterexample is to over-optimize on one dimension. So the current endpoints API sort of is the counterexample. It basically optimize on one dimension, that is the number of objects. So each service only corresponds to one endpoint object, and the endpoint object has to contain all the endpoints. So the high-level idea of the redesign is to slice up the giant endpoint object into multiple objects called endpoint slice. It's very similar to database sharding, but with some Kubernetes-specific flavors. So first of all, the endpoint slice contains 100 endpoints. We're going to talk about why we pick 100. And it's going to be configurable via a controller flag. And a new controller called endpoint slice controller will be implemented to automatically manage the life cycles of the endpoint slice object. Since one service corresponds to multiple endpoint slice objects, so the naming scheme we will not reuse the existing endpoints naming scheme. The existing endpoints just share the same name with the service. And instead, the endpoint slice will use a generated naming scheme similar to the pods behind a replica set. And also, we maintain the endpoint slice mapping using a label on each endpoint slice object with the key pointing to a service and the value pointing to a service. So let's go over the endpoint update in this new API. So let's say, obviously, all endpoint slice has to be sent to all kube proxies at first. If there's no update, nothing happens. Let's say there's one update, one endpoint update in the service. So only one endpoint slice will be updated, and that slice will be distributed to all the kube proxies. And there are more details. So this is the future extension we want to enable in the API, is that each endpoint can actually contain multiple IPs. So in the old endpoint API, each endpoint can only hold one IP that corresponds to the pod IP. So as part of the IPv6 effort, pod IPs are getting pluralized. So each pod can have multiple IPs, and endpoint slice API can express that. So that gives us dual stat support on day one. And the second point is that each endpoint have extensible status. So the current endpoints API only has a binary status per endpoint that is ready or not ready. So as the kube proxy, the ready and not ready correspond to the pod readiness. So based on the current API definition, it's very hard to extend beyond this binary status. So in the new API, we treat it as a struct and make it more easy to extend the endpoint status. So as the consumer of the endpoint API, endpoint slice API, which is particularly kubeproxy, as the kubeproxy gets more sophisticated, we can feed the kubeproxy with more richer information, like for instance, connection draining state or something else that the kubeproxy can handle. And at the same time, this extensible status structure can also maintain the backward compatibility. So let's say an older IPtable-based kubeproxy only handles ready, then you just need to care about readiness, right? You don't need to care about whether it's like connection draining or not. All right, let me hand back to Wojtek.
So now let's talk like how we were or how we are evaluating the design to ensure that it will really meet our expectations. So first, let's talk about what scenarios we are talking about. So the first one is update of a single endpoint in the service, the rolling upgrade of the whole service, all endpoints in the service, and creation or deletion of a service. They are pretty much the same, assuming that all the pods underneath still already exist. So those are the scenarios. What about metrics that we are talking about? So there are basically two groups of metrics that we are focusing on. The first one is originating in etcd, and the specific metrics we are looking at is number of mutating API calls, so number of writes in etcd. In our case, it's basically number of endpoint status, endpoint slice or endpoints in the current implementation update. And the second thing is size of the individual object. The second group of metrics is oriented around watch. We already have seen why watch is so crucial. And the specific metrics are number of watch events per watcher, total number of watch events across all watchers, and total number of data that we need to transmit via watches. The last two can be actually computed on the first three, but we are showing them just to show what scale we are talking about, and they are really eye-opening to see what numbers we are talking about. So as an evaluation case, let's take a look into some large example that we would like to support. The case is 20,000 endpoints in 5,000 node cluster, and let's say that B is the number of endpoints per endpoint slice that Minhan was talking about, the new object that we are going to introduce. And the scenarios that we are going to evaluate is the current design with single endpoints object, the scenario with 100 endpoints per endpoint slice, and the scenario with 1 endpoint per endpoint slice. So in the first scenario, of update of a single update of a single endpoint, the number of writes actually doesn't change. There's always one write, or roughly one write. But the size of the object obviously changes significantly. Currently, it would be roughly 2 megabytes. With 100 endpoints per endpoint slice, it would be 10 kilobytes, and here it will be less than kilobyte. Here nothing really changes, but as a consequence of much smaller object with endpoint slides, then total number of data that needs to be transmitted changes from 10 gigs to via 50 megs to less than 5 megs. So that's a single endpoint update. What about rolling upgrade of a whole service? Here the number of writes changes significantly because we need to do roughly one write per event. So we get 20,000 writes basically. Size of the API object changes the same way as in the previous case, obviously. So as a result, what we get is that the total number of bytes transmitted is changing from 200 terabytes via 1 terabyte to less than 100 gigabytes. It's a bit funny that we are talking about like less than 100 gigabytes. We are not really caring whether it's like 50 gigabytes or like 70 gigabytes, but it only shows like the scale we are talking about here. We only care about like order of magnitude of like hundreds of gigabytes really here. So the first scenario that, which is like service creation that I mentioned before is slightly different than the previous two. The number of writes in the current implementation will be roughly 1, but with the endpoint slice object, it will be significantly more because we need to, on service creation, we need to write all the necessary endpoint slice objects at once. So with singular endpoint object, it will be like 20K writes. With 100 endpoints per slice, it will be like 200. Size of the object changes the same way as previously. So as a consequence of those two and the fact that number of watchers doesn't really change in any of these scenarios, the total number of watch events changes from like 5,000 to via million to like 100 millions. But the total number of data that needs to be transmitted remains roughly the same across all those like 3 cases. So we are generally saying that, or recommending to create a service first before you create pods and that. So that scenario seems to be like the least important one. So, and then in the previous one, as I showed, like the smaller the endpoint slice object is, the better it looks like. So why we are actually proceeding with like endpoint slice thing? So there are a couple of reasons for that. The first one is that for small services, let's say smaller than 100 endpoints, there is no conceptual change for users. So there will still be like one endpoint slice object. So there is still this correspondence of one object to one endpoint slice object to a service, which means that users don't really need to think about or don't really see the change here. The second thing is that with singular endpoint object, like there won't be a way to like batch the updates if many things are changing at the same time, which is also like a significant performance improvement. And the third one is like the last scenario that I mentioned, which is like creation of a service where we have much higher amplification of mutating API calls, which is one of the most important limiting factors for scalability of the system. So one thing that I would like to mention here is the API here is very, very generic. So if at some point like scalability characteristic of Kubernetes will change and it will be more efficient or more optimal to keep all the endpoints in a single object or just have a singular endpoint object, we can actually change the logic of the controller without any API changes, which is like very, very powerful or a very important argument for this API. Yeah, that's not all. So with that, I'm handing over back to Minhan.
So with all that, is that the best we can do? So what else can we achieve with this endpoint slice API? So like with the current proposed solution, the incremental updates per endpoint becomes much more efficient. So it's efficiently calculated, stored, and transmitted to all the nodes. But the bottom line is that we are still sending all the endpoints to all the nodes. And each node will still have a global view of the service endpoints. So this will cause the scalability problem like on the next step. So how can we avoid sending all the endpoints to all the nodes? So here we have the next step of the evolution, which is the dynamic endpoint subsetting. So by only sending a subset of the endpoints to a group of nodes, we effectively reduce the per node overhead and also further reduce the transmission overhead per endpoint updates. And the new endpoint slice API is fully capable of expressing this schema. But however, since the goal is not to enable like 1 million endpoint behind a service, the goal is to enable tens of thousands of endpoints behind a service. So it's not urgent to implement this kind of like mechanism, and we soon realized that it's actually very hard to implement this. So the key of the problem is that we do not know the client source. So like today, all the endpoints and all the services are distributed to all the nodes, and kubeproxy program all the nodes to forward traffic to the services. So wherever the client is, they can reach the backend. But however, if we do subsetting, only, let's say the clients are only clustered like in a portion of the nodes, then that will cause like the backends to receive imbalanced traffic, and even for the worst case, some backends will not even receive traffic because the subset is not, like their endpoint is not exist on the certain nodes, right? So to avoid like this imbalance problem, we have to introduce some kind of overlapping. So here in the endpoint slice, you can see we actually have one endpoint in multiple slice, endpoint in multiple subsets, and then they are programmed on different nodes. And this also brings some downside of write amplification. That means one endpoint update, instead of only updating one endpoint slice object, we have to update multiple endpoint slice object. And it gets gets like complex very, very quickly. So at this point, the complexity doesn't justify the gain. So we decide like not to do it at this point. But if the time is right, the requirements there, the API is ready to like meet the need and go even further. All right, that concludes our presentation. So we can take questions now.
Just lift your hand if you have a question.
Hello, and thanks for your talk, first of all. My question would be regarding the updates from endpoint updates with IPtables. We're seeing with huge amounts of services and endpoints that there are a lot of updates to the IPtable rules. Are there also some kind of structural plans to lighten the load on the systems regarding the IPtable rules?
Sorry, can you repeat the second part of the question? I didn't hear the last words.
Are there also suggestions on how to solve the amount of IPtable rebuilds that we are getting when you have huge amounts of endpoints?
So this is kind of separate problem. Like, we admit it is a problem. But it's also like a slightly different problem. We don't want to mix those two together. Like, we can solve them completely separately. There are some ideas like what we can do here. Like, Minhan probably can talk a little bit more about it, but like IPVS or using other things instead of IPtables are something that we are considering. IPVS actually is GA already.
Yes.
Support. So it may mitigate those. We are also looking into other solutions here. I don't think we made our mind here, like what is the desired long-term solution, unless I'm missing something, but I think we didn't, right?
Yeah. So the short answer is the IPtables is very dependent on the kernel, right? So some kernel performs better, some versions of the net filter performs worse. So from what my impression is that like a good well-performing kernel can handle millions of IPtables rules like easily. So it still hasn't, we haven't like reached the scalability limit of IPtables. Yeah, so when we get there, so there are always other options, IPVS, eBPF, like other implementation of kube proxies. Yep.
Hi. First, thank you. That was a really nice talk. Some of the services we run currently have between like 500 to 1,000 endpoints. We haven't seen any of the performance limitation yet, but probably we weren't looking in the right place. So I'm definitely going to check that. What would be your current recommendation for people reaching this scale to slice things so that they, while we are waiting or while we are working on making this implementation, what can we do to not reach those problems?
So I think that it also depends like on this, like it very significantly depends on the large of your cluster. So if your cluster, say, has hundreds of nodes instead of thousands, like the problem is much, much less visible. So one potential mitigation, if it's possible, would be to like somehow split your clusters and ensure that those large services are running in smaller clusters. If the control plane will be provisioned with enough resources, then that would like hopefully be sufficient.
Yeah. Okay. And there's some other tricks like storing your endpoints object in a separate XCD so that they have a dedicated XCD to like which is more scalable and better like monitored. Yeah. So.
Yeah, or provisioning more API servers. That's also one of the mitigation, because like one of the limitations is like how much data API server has to process. So like having more of them means kind of sharding the work between those, right? So.
Hey, so you basically seem to have sharded the collection of all these endpoints into endpoint sets per se, and the other problem you're facing is distributing the data itself. So why not use something like, say, multicast or some sort of reflectors that are popular in BGP to actually shard out, transmitting this data over to each of the slave nodes? Like, if you could, instead of retransmitting all that data to each one of the nodes, through the API server, you have some sort of a proxy just to maintain endpoints, and you shard that send out of the data, and maybe use multicast where you can allow that with some sort of thing. That might help reduce that problem.
So is the question that basically whether we should use a proxy, right?
Yes, some sort of dedicated proxy. It might mean changes to the API layer, but just this distribution problem that you have to solve that bit.
So yeah, that's one of the potential mitigations, but it sounds more like mitigation, right? So like, it's probably worth trying if someone needs to do it urgently, but we wanted to solve it like properly in the API too. So, and also like we were starting this effort with hope that we will do things like dynamic subsetting from the early day, which will help for other problems, like for example how big the IPtables actually are. But it appeared that there are a bunch of hard problems that would need to be solved that would make this solution like taking 5x more time or something like that, and like we decided that let's not do everything at one step. But
hi. So it seems like the conclusion to draw from your examples, right? With I forget what the difference between one and the other was, but in the end it was that choosing 100 didn't have optimal bandwidth usage, or let's say transit usage, but it had better number of events, right? Mm-hmm. It had a better number of events than using a single endpoint. So what is the metric that is affected by number of events? And even when it's 1 million, doesn't it add like a latency problem? Or is it concurrent enough that, like what's my question? What metric gets worse when you have a lot of events?
So basically, there is some overhead per event. So in particular, in event you are sending the Kubernetes object which has like metadata and stuff like that. So there is like some overhead per event. So the more you like, even though we are actually saying that like
because here we can see 100 endpoints per slice, it doesn't have optimal transit, but in the next scenario, it has better total events.
Yes.
Right, slightly better, but it's still worse than existing endpoints. But obviously the bandwidth is intractable with existing endpoints. So
imagine like after you create a service, like let's say because all these controllers have rate limiting, right? So like imagine you create a service and then selects a large number of endpoints, and your whole like controller, because it's running in the controller manager, it's going to share the rate limiting, and the whole controller manager we're going to just host for several minutes to creating these endpoint slices. Like if you only have one endpoint per slice, right? So that's something that basically what we lose is that we lose the capability of batching. Let's say if you're rolling update and you have like you change 10% of your pods instead of one by one, then the controller can actually have some tricks to batch it. But like if you only put one per slice, then there's no way we can optimize on it. Yeah.
So there's also like on API server level, we are processing like, there's at some point we are doing a little bit of processing by serializing events, like one event at a time. So the more events you have, the more contention you are getting in this small point. So there are a bunch of things that we can do there to improve that. So, but yes, we are far from being there also.
Hello, thanks for the talk. A simple one, how I can follow up just after the conference with your solution? I haven't seen any links to GitHub or any issue scapes. With your solution and what you're going to do after. So like you described the issue, you have some proposals, and you're saying the further steps, what to improve. So I don't know, in months or two, just where I can see the information.
So what is happening now is that we shared this and discussed within Scalability and Networking 6. There is a doc describing that. It's almost in the form of a CAP, but it wasn't yet has been opened as a formal CAP in the repository. But it will happen probably within days or so from now.
Yeah, the doc's just easier to comment. You don't want it to have a PR and then tons of people comment on it. All right.
So yeah, but in general, we will be targeting like 1.16 for alpha implementation for that.
If a service scales up and down during the day, you might have many slices that are getting empty and others that are full. First, is it a problem? And second, is the direction to start doing rebalancing between slices to rebalance those numbers?
Yes, so there will be rebalancing. So like, let's say the existing slices cannot handle new endpoint, obviously we just create new slices. And then if you, like the number of endpoints just shrink, and then like the percentage of a slice has less than, let's say, 20% endpoints, then we trigger the rebalancing. But like, it's really depending on what algorithm we wanted to use. So this type of algorithm is pretty mature, so we can just get it off the top of the shelf.
Also, like the advantage of like this rebalancing is that we can really do that when there's a bit less work to do, other work in the system. So we can we can offload it for later if really needed, if we have a lot of higher priority work, let's call it.
Hi. So we're doing some things like we have services which have no selector, so we're manually populating the endpoints. How is it going to fit in this model?
I'm not sure I understood.
So we have a service, and service has no selector, so we manually populate the endpoints for the Kubernetes service. So will it work with this model or not? And if, like, so we'll manually have to manage the slices and so on.
So sorry, to clarify, like, is the question what to do with manually managed services?
What's going to change, yes, in this case? Like, now there is just one slice. I just populate the endpoints, right? Then I have a Kubernetes service which has no selector.
So the service, Kubernetes service itself, it doesn't change? So we are not changing the Kubernetes service spec with this new API. So this is mostly for Kubernetes internals, which is kubeproxy in particular. So the other consumers of the existing endpoints object, we're going to keep running the endpoints controller, and then whoever is consuming it can keep consuming it. But we're going to apply some kind of a limitation on the old API and say, hey, if you grow beyond this amount of endpoints, so you need to use the new API. So from the service itself, there's no change. So there's no usable, user facing change on the service. So, and that's one of the goals we wanted to achieve in this redesign, is that it should be independent of whether we wanted to change the service spec. And ideally, service v2, the next version of a service API, should just work with the new API.
Okay, last question. Otherwise, I would ask you to take it to the hallway track.
Hi, thanks for your talk. I have one last question. So you mentioned that there will be no changes on a service definition level. So how are you going to define or determine the size of needed slice for endpoint? So who will decide how it will be configurable, or will be configurable some other places? So you want to split endpoint to different slices. So what about size of the slice? Who will decide? And
so we will be recommending, probably we will end up with 100 or something around that. In general, I wouldn't expect anyone to play with that unless they have a very good reason and very specific use case and stuff like that. But yeah, I wouldn't expect 99.9% of users touching it at all.
Okay.
Thank you. If you have more questions, I guess these two gentlemen will be available in the hallway. Thanks.